So good afternoon all. My name is Swati. I work at SSIR, Samsung Semiconductor India Research Facility at Bangalore. And today I'll be presenting our work on building an object-based STaaS solution with Samsung's Poseidon project. This is the agenda. And in this talk, first I'll be introducing you to the Poseidon project, followed by some of the work that we have been doing in our lab to build an object-based STaaS ecosystem on Poseidon. I will present the benchmark numbers that we obtained for the STaaS deployment. So this is an introductory talk, and this work is recently started. I'll be covering some of the basics on many of the object storage related concepts and present some demos in the end to showcase these concepts in detail further. So let's start with the overview of Poseidon. Poseidon is an open source NVMe fabric solution developed by a joint collaboration between Samsung, Inspur, and Naver Cloud, and is targeted for cloud and hyperscale data centers. So Inspur is a server technology giant from China, whereas Naver Cloud is a cloud giant from South Korea. Naver is basically the #1 search portal in South Korea, and it's similar to Google Cloud. The software part of Poseidon OS is maintained in GitHub as an open source project, whereas the hardware from Inspur is already available and is compliant with the OCP specification. Poseidon hardware supports a composable architecture based upon the U.2 E1.S, E3.S SSD form factor for enabling storage disaggregation using NVMe fabrics. Since the Poseidon system is co-designed for both hardware and software, it commits to provide all the vital features of the NVMe fabric protocol. Poseidon OS, also called POS, is the software part of the Poseidon project. Basically, POS is a lightweight user space storage operating system for NVMe-oF. As shown in the figure, POS runs as a user application. This is the POS OS. It runs as a user application on Linux kernel, and it can provide customized virtual devices to the initiator via NVMe over fabrics. These devices are discovered as virtual block devices in the initiator side. It provides PCI Gen 4 performance via network over a 200 gig connectivity. And it supports various storage features, for example, NUMA awareness, volume management, performance throttling, RAID, HA, etc. All the SSDs in Poseidon are managed as a RAID array. Hence, error management is possible, and data is available even when the SSD failure happens as part of the fault tolerance from RAID. It supports high availability and can also be consumed by the upper orchestration layers by means of RESTful APIs and CSI driver. So Poseidon exploits the benefits of NVMe SSDs by optimizing the storage stack and leveraging the state-of-art high-speed interface, which is available in the hardware. It implements software-defined storage capabilities to meet the various needs of storage applications in a data center. With POS, hyperscalers can easily build composable disaggregated infrastructure in their data centers. The latest version of POS is 0.11.0, and it is released in GitHub. This is the GitHub link. Let's look at some of the goals of the Poseidon OS. The goal of POS OS is to provide high performance at volume level for each of its clients. QoS of quality of service is provided in the form of a stable performance at each client at a volume level, since all the SSDs are managed with RAID. It is a highly available system. It eliminates single points of failure to ensure continuous operations. Currently, it supports 2-node high availability and data is guaranteed from even software or any hardware errors. The maintenance of POS OS is done using the CLI commands, as we saw earlier. There is a CLI interface available, and also the maintenance can be done using RESTful APIs. So now that we have introduced the Poseidon project, there have been some earlier talks also in Poseidon, and it is already available in SDC channel. Let's talk about STaaS. So what is STaaS? Today, CSPs, basically cloud service providers, are constantly challenged with large volumes of data and increasing demand from customers for cost-effective storage. So to solve these challenges, they provide software-defined STaaS solutions for exposing the data as a service by abstracting the storage software from the storage hardware. STaaS services can be deployed with either object or block or with the help of file storage. Today, mainly CSPs in our research, what we believe are adopting object storage as their primary storage service for building their cloud storage infrastructure, as legacy storage systems based on file and block storage are limited in their ability to scale. And also these traditional storage architectures struggle to manage high volumes of unstructured data. Object-based STaaS service is also becoming popular, as object storage is today the dominant class of storage for the cloud. So our goal is to build an object-based STaaS platform optimized for Poseidon storage. We did a study on the STaaS deployments currently available in the market. In our study, we found that most STaaS deployments available in the market are based on a monolithic architecture that can be seen on the left, with no support for cloud features like multi-tenancy and orchestration. In monolithic systems, multi-tenancy is achieved by supporting multiple users and is not a true kind of a multi-tenancy. The storage nodes are partitioned for multiple users based on users, groups, roles, and policies. Orchestration and isolation of the storage is done by the storage layer itself. So this architecture works well for a very small scale deployment, but fails to scale as the number of tenants increase and is not suitable for the cloud. To truly become cloud scale, storage should be deployed with true multi-tenancy, and isolation and scaling of tenants should be done by the cloud orchestration platform, for example, Kubernetes, which is very popular, and something like this, as shown in the right. And this is a cloud scale architecture. Kubernetes is doing the orchestration and management of these multiple tenants. So next, I'll demonstrate how we have built a unique cloud scale object-based STaaS platform based on Minio object storage. Minio is an open source platform, and it supports both these monolithic and cloud scale architectures. We have chosen Minio as it is quite simple to use, it is open source, and yet it is immensely powerful and scalable. So now I'll walk you through the Minio object-based STaaS solution that we have built on Kubernetes platform with Poseidon as its backend storage. So this is a diagram. This diagram here presents the deployment of our multi-tenant STaaS solution with Minio object storage. Let's go from the bottom. So the backend storage is configured as Poseidon target. The Poseidon volumes are mapped to the Kubernetes nodes and are presented as direct attached storage devices to Kubernetes. This is done with a direct PV CSI driver, which is available from Minio. So the direct PV CSI driver helps in formatting and management of these pool of drives, which are coming over an NVMe-oF protocol from Poseidon. And these drives are made available to all the worker node and marked as ready. So all this is done by the direct PV CSI driver of Minio. We are also making use of Minio operator, which is basically a Kubernetes plugin to achieve the multi-tenancy. Minio Kubernetes operator plugin simplifies the deployment and management of Minio object storage on Kubernetes. It is mainly responsible for creating multiple tenants and their management. Minio also provides a Minio console, which is a very simple and intuitive web interface for creating a Minio tenant. So what is a tenant? What is a Minio tenant? Sorry. So a Minio tenant essentially represents a Minio object storage cluster, which means when we create a Minio tenant, we are creating a pool of servers. Inside a Minio tenant, let's say I'm creating a tenant. Inside that, I can specify how many servers I need to run in a particular cluster. So when I create a Minio tenant, essentially I'm creating Minio server pods that are deployed in the Kubernetes cluster as the nodes of the Minio tenant. Each server pool is an independent set of nodes with their own compute, network, and storage resources. In multi-tenant configurations, each tenant is a cluster of basically server pools that, while they are sharing same physical infrastructure, they are fully isolated from each other in their own Kubernetes namespaces. We will see this in more detail in a demo later. So we can configure multiple tenants within the same Kubernetes cluster. For example, in this diagram, we have two Minio tenants, tenant 1 and tenant 2. Each tenant can have different capacity, resources, and servers, as well as separate configurations like encryptions and versioning and security. Each tenant is fully isolated from each other in their own namespace while sharing the same physical infrastructure. Each tenant can also scale independently and have the ability to protect themselves from any disruption or update or security incidents occurring in any other tenant. Essentially, this gives us a true multi-tenancy architecture on Kubernetes. We have also set up a Docker repo to pull application images for running various workloads like AI/ML, data analytics, and data ingestion. The Docker repo helps us in hosting these applications on the Minio tenant. Finally, to collect system statistics and system metrics, we are making use of various services. For log collection and system metrics collection, we are using Prometheus service. And to back up the Kubernetes pods and Kubernetes deployment, we can make use of Velero service. Both of these are Kubernetes services which are available with Minio. Let's look at some of the performance benchmarking that we did on the Poseidon STaaS. So we have used the WAP benchmark. This is a S3 compliant object storage benchmark. It supports S3 protocol, and it is developed and maintained by Minio. It supports a rich set of configurable options, using which the test data and the workload can be tuned to be close to real-world conditions. For example, it can be configured to run with different size of objects, number of parallel threads, enabling and disabling of TLS, and many other parameters to represent the workload. So this is one of there are a couple of popular benchmarks. One is the S3 benchmark available again from, I think, Minio. WAP is another popular choice for object storage performance benchmarking. So testing of one or more Minio hosts with one or more WAP clients, right, like this, can be done in a coordinated and automated way by using a WAP distributed benchmarking. What is meant by distributed benchmarking? Here we can see that multiple WAP clients are running in a distributed fashion as a cluster, and with the help of this WAP server, right, we can pump traffic to all the S3 server nodes. So to run the distributed WAP benchmark, we have created a 4-node WAP cluster. Each WAP cluster node of the each WAP client node of the WAP cluster can generate traffic to all the Minio cluster nodes simultaneously. So as I mentioned earlier, Minio can be configured both in standalone monolithic mode and cloud scale mode on Kubernetes. This particular deployment is a standalone mode where each Minio server is running in a physical machine. All these are like separate physical systems. So this is a monolithic deployment. We are checking this deployment so that we can compare it with Kubernetes STaaS deployment later. So in this figure, we can see that it has 4 Minio nodes in a cluster with backend volumes coming from Poseidon. Poseidon targets. There are 4 different targets which are connected. All the 4 Poseidon targets are connected over a 100 gig network switch, and each WAP client, which is again running in a cluster, is pumping the benchmark traffic with a 100 gig network switch, network interface. So the expected performance for this setup is around 40 to 45 GB. The calculation is written here. We have 400 GB interfaces, so the total is around 400 GB, which comes to 400 gigabits, which comes to 50 gigabytes. And similarly for write, since we have enabled eraser coding, there is a certain drop, and the expected theoretical performance is around 25 gigabytes per second. These are the theoretical numbers, but since we are using NVMe over TCP protocol, the expected numbers will be slightly lower, considering some overheads caused by the protocol. So the expected numbers for read are around 40 to 45 GB gigabytes, and for write it is 20 to 23 gigabytes. So in this setup, we achieved, we did some performance benchmarking, and we achieved around 42 gigabytes for the read path and around 23 gigabytes for the write path with an object size of 1000 MB. Now let's see the setup for Kubernetes STaaS, which is also called Cloud Scale STaaS. We have set up a Kubernetes cluster with 4 worker nodes and 1 master node. These are the worker nodes. Each worker node is an independent physical system. Each of these 4 worker nodes have Poseidon volumes configured as the backend. There is one-to-one mapping happening between each Poseidon target and the worker node. And the connectivity between the worker nodes and Poseidon target, each Poseidon target is again 100 gig. And again, we have configured WAP. The WAP cluster is running basically inside the Minio Kubernetes cluster as WAP listener pods. This also we will showcase in a demo later. So this entire connectivity is again 100 gig. Even the connectivity between the inside the cluster, which is shown in red, is also 100 gig. So the cluster communication is also happening over 100 gig. So since this Kubernetes setup consumes similar hardware and similar resources as the standalone setup we saw earlier, we are expecting similar performance numbers, maybe slightly lesser considering the Kubernetes overhead. So these are the numbers that we obtained with our WAP benchmark. The maximum numbers that we obtained for the read path are 29 gigabytes, and for the write path are 23 gigabytes. The write performance numbers are quite comparable to the standalone mode. Read performance is little less. It's around 10 GB lesser than the standalone mode. And currently we are discussing with Minio team to root cause where the issue might be. These are our initial findings, and we plan to improve the configuration to get some better numbers and results. Finally, on the Poseidon STaaS, we also tried to deploy a machine learning pipeline to evaluate it further. We have deployed a 4-stage modular ML pipeline. So to understand what is meant by modular ML pipeline deployment, let's first see how a traditional ML pipeline is built. So a typical ML pipeline consists of multiple stages. First, the data set to be trained is downloaded and extracted. The extracted data is then pre-processed for the training phase. Next, the required ML model is trained with the test data set. Once the training is completed and the model is evaluated, it is deployed, and the model starts serving. As the deployed model serves, with time we acquire more and more data, and as the new data is coming, this training model needs to be retrained, because maybe the data set that we trained it against earlier may not be ready with the newer data set. So this is the cycle basically maintained in a traditional ML pipeline. So typically for deployment, ML deployments, these different stages are bundled in a container or a virtual machine. This limits the, so when we do that, we see certain limitations. So what are those limitations? Let's discuss that. So when we deploy these various stages in multiple containers and virtual machines, the model is limited to run continuously. And why is that? Because the data has to be copied and moved for each and every stage. The data is local to every VM, and for processing in every stage, the data has to be continuously moved. Retraining the model with any newly acquired data is cumbersome, as again we have to copy and transfer the data to the tightly coupled storage. And also as the data set grows, the compute gets busy in fetching, and extracting the data, rather training it. Generally, the compute in machine learning consists of CPUs and GPUs and sometimes expensive TPUs, is sourced from the cloud and is quite expensive. So, which leads to basically wasting expensive hardware. So, to solve these challenges, what we believe is we can use a common shared infrastructure with object storage. Object storage can be deployed as the storage infrastructure for this ML pipeline to load all the data on demand for each stage. So I'll just give a very basic example with a small data set where we have built a 4-stage AI/ML pipeline on the STaaS solution that we deployed on Poseidon. So there are many open source machine learning datasets available. For example, the ImageNet dataset, which is used for image classification, and it consists of a large dataset of about 1.3 terabytes. For testing purpose, we took a smaller dataset, which is available from, I think, Stanford. The dataset is called Large Movie Review Dataset. It mainly does sentiment analysis. It evaluates multiple movie reviews for sentiments, like whether the review is positive or negative. So we deployed a ML pipeline with the sentiment analysis dataset and integrated it with the Minio tenant that we deployed on Poseidon STaaS. By deploying Kubernetes Minio as the storage infrastructure for this ML pipeline, we mainly achieve a modular ML pipeline consisting of 4 different stages, with each stage using the shared Minio storage for storing and retrieving the data. As we can see here, each stage of the pipeline interacts with Minio and loads and stores the desired data on demand to and from Minio as shown in this figure. First, the data set is uploaded. I'll just walk you through the multiple stages. So the first stage is we need to download the data set and we need to extract it. So in a traditional approach, we'll probably have a VM in which there'll be some local storage and the data set will be downloaded and extracted, and it will be bound to that particular VM. Here what we do is we have a shared Minio bucket and we download the data set and then upload it, extract it and upload it. Once that is done, we set all the configurations and dependencies. Then the data set is downloaded from, again, Minio bucket for pre-processing. And what we do in pre-processing is we convert this data. This data set is again stored in terms of object, right? So we convert these object records in something called a TensorFlow record, TF record, and upload it back to Minio. So the saved TF records are loaded for batch processing during the training phase of the model. Basically, this is an optimization. Using this pre-processed data, the training will be faster. The safe TF records are, once they are trained, the training checkpoints of the model as well as the TensorFlow, TensorBoard histograms are saved in the Minio bucket again. Finally, when the model is trained and it completes, the completed model is also saved to the Minio bucket. So what we can see is for each stage, we are utilizing a shared Minio bucket, and the data is available for each of these stages, which makes it modular. So by doing this modular approach, it helps in solving all the limitations that we discussed earlier. We are not wasting compute in fetching and extracting the data sets, the data, or moving it across the different stages. It's already available in a shared infrastructure enabled by Minio. So I do not have a demo to show you the running pipeline, but this is a very simple script which is to enable this entire ML pipeline, right? The entire script is available in GitHub. This is the GitHub link. And it's a simple script. Inside the script, some small modifications have to be done. The primary modification to enable the script to, the current script is mainly written for standalone deployment. To enable it for, to integrate it for Minio tenant, we need to change the Minio address and access keys of the Minio tenant and make some minor modifications. This slide is not very clear. So once the script runs and the ML training completes, right, we should see something like this. These are screenshots from the Minio bucket. This is the Minio console, and this is the data set. At the first stage, we are loading the entire training data set in the Minio storage. Once the data is loaded, we are pre-processing the data, and the pre-processed data is also again loaded back to the Minio bucket. As the training progresses, all the checkpoints are also again loaded back to the data set. And once the training completes, the saved model is also loaded back to the data, to the Minio bucket. So mainly we need to confirm that data has been copied to the Minio bucket for different stages. So before we conclude, I have two simple demos to demonstrate how to create a Minio tenant with Minio, and also how to run the WAP benchmark. Just a sec. So I'll start with the demo. In this demo, I'll be showing how to deploy a Minio tenant with the help of Minio operator. So to begin with, we need to have a Kubernetes cluster. So this is a 4-node Kubernetes cluster with 4 worker nodes and 1 master node. These are the worker nodes. Now on one of the worker nodes, basically on all of the worker nodes, we need to do a NVMe connect to discover the Poseidon volumes over NVMe-oF. So we have connected to the Poseidon target, and these NVMe devices are coming from Poseidon Storage. Totally 8 devices are coming per worker node. Now we will make this storage, NVMe storage, available to the Kubernetes cluster with the help of the Minio DirectPV CSI driver. So what this DirectPV CSI driver will do is, it will manage these NVMe volumes and make them available to the Kubernetes cluster. Once the drives are marked as available, they have to be made ready to be consumed by all the worker nodes. Now, at this point, we are initializing the Minio operator. And as we were initializing the Minio operator, we get this proxy tag, which we need to supply to the Minio GUI to enter the console. So since we initialized the Minio operator, we can see all these Minio operator pods up and running in Kubernetes. Now let's go to the master node, and we got this tag. Sorry, it's very small. Yeah, this is the tag that we need to enter to the GUI to as a credential. And once we enter that passcode, we enter the Minio operator console. So making a tenant is quite easy. This is the create tenant wizard. So to create a tenant, we need to specify all these values. So we have to specify the name of the tenant, the namespace. For each Minio tenant, we have a dedicated namespace. In one single namespace, we can only have a single Minio tenant. We have to select the storage class as DirectPV Minio. There is another storage class available, which is the legacy class. It's called Direct CSI Minio. Now we have to select how many, as I said, inside the tenant, basically you are creating a Minio server cluster pool, Minio cluster with a pool of servers. So in this particular tenant, we want to give 4 servers. We want to create a server pool of 4. And to each server, we are specifying 4 drives. So totally 16 drives will be, 16 drives are specified. Considering each drive to be of 2 TB capacity, the total size of the tenant would be 32 TB. Eraser code can be selected. We have selected set eraser code to be EC4 for all our benchmarking. And we can also specify resources, CPU and memory resources for the pods, Minio pods. So all these settings will be updated here. Apart from that, we can also select several other configurations like images, pod placement, identity provider, security, encryption. We have turned on TLS for benchmarking. We can, for collecting logs and monitoring, we need to again specify the DirectPV Minio driver. And we can simply do a create tenant. This is the credentials for the tenant, access key and secret key for the tenant. And a new tenant is created. It is initialized and the health is green. We can go back to the console. And also for each tenant, we have these matrices available. We can see how much is the usage, the traffic, and resources utilized by this Minio tenant. On the master node, if we check all the namespaces, we can see that for the tenants, since we created a tenant with 4 servers. We can see a tenant pool with 4 pods, tenant pods, and also another pod for Prometheus for data collection and logging. Okay. Yeah, these are the server pods, and this is the Prometheus pod. These are various other pods created, services which are created for managing this Minio tenant. And similarly, we can create multiple tenants. The tenants created, we can create another tenant by clicking on this. So these tenants are truly independent of each other, though they are using the same underlying physical resources. I have another demo to benchmark this created Minio tenant. Yeah. So to benchmark this tenant, we are using WAP Benchmark. So the WAP benchmark is quite simple to set up. It is available in GitHub. Mainly it consists of 2 YAML files. The first one specifies the number of WAP clients that we need to configure. And the second one basically contains the job that this WAP benchmark has to issue. It's a small demo. We'll just quickly see it. So this is the WAP YAML, and we have to specify the number of WAP client pods that we need to create, listener pods. So we have specified 4, and the port on which this WAP benchmark WAP clients will run, WAP listener pods will run. So we're starting the WAP YAML. We have created these many WAP listening pods. These are basically the WAP clients which can generate I/O to all the Minio servers or the Minio tenant. And then in the WAP job file, the second configuration file, we need to specify the tenant address, the access key to access the tenant, and we have to specify the job, the workload that we want to generate. So in this particular example, we are running a get workload. Get is mainly equivalent to read in block storage, and we need to specify a couple of parameters. So this is a get benchmark. This is the Minio bucket that WAP will consume. We have configured 4 WAP clients, so we need to specify their address. And we need to specify the Minio host, the tenant, which is consisting of, again, 4 server nodes, and the Minio service. Also, we can specify how many parallel concurrent threads we need to launch, and also the object size with which this benchmark should run. In this case, the object size is set to 512. In our benchmarking, we have tested with 1000 MB. So let's create this WAP job. Once the job is created, we can see it running. And the test has started. And we can see that for put, which is essentially write, we are getting 23 gigabytes of performance, and for get, we are getting around 28 gigabytes. The earlier number that we showed was with 1000 MB, so it was slightly higher. So this concludes both our demos, and I'll come to the conclusion. Yeah. So in conclusion, in this talk, we demonstrated how we have built a low-cost cloud-scale STaaS deployment on Poseidon Storage using all open-source technologies like Minio, Kubernetes. We also successfully utilized the Minio operator on Kubernetes to deploy a cloud-native STaaS. And also we demonstrated that we achieved quite comparable performance with Kubernetes STaaS as compared to standalone STaaS deployment. The read performance is something we are still discussing with Minio, and hopefully we'll be able to improve it over time. This concludes our this presentation. These are my co-authors who contributed to this work, and we can be reached in this mail ID. Thank you.